Picture this. You're in a contest. Someone hands you a sheet of paper covered in numbers, from 1 to 1,000. The challenge is to circle every prime number as fast as possible. No hints, no calculator, just you, your brain, and the clock ticking. You begin by identifying the easy ones, 2, 3, 5, 7, 11, 13, and so on. But the further down the page you get, the harder it becomes. You see, primes don't announce themselves or appear in any discernible pattern. At first glance, they appear entirely random, taunting you at every turn. But could there be a formula, a way to predict where they'll show up? Or could there be a way of predicting the frequency with which they occur? These questions have obsessed mathematicians for centuries, because the distributions of primes looks random, but somehow deep down, it feels like it shouldn't be. Surely there must be a law, something that governs how often they appear. And in 1792, a boy just 15 years old became captivated by this very question. His name was Carl Friedrich Gauss. With nothing more than a notebook, a pencil, and a burning curiosity, Gauss began counting primes, not just in the first 1,000 numbers, but in the next 1,000 and the next after that. He recorded them, hunted for patterns, chased a glimpse of order in the chaos. What he found would change mathematics forever. But before we can follow his trail, we need to understand the nature of the problem he was wrestling with. What makes a prime so different from any other number? And why has the search for them challenged the world's best mathematicians for over 2 millennia? Every grand structure, from the tiniest crystal to the largest spiral galaxy, is constructed from basic building blocks. Physicists have quarks and leptons, chemists have atoms, and mathematicians have something just as fundamental, the prime numbers. But what is a prime number? Ever find yourself stuck like this for hours? I do, especially being tall. I spend way too much time leaning over, and at the end of a long day, my back lets me know. That's why I switched to the FlexiSpot E7 Pro standing desk, and to be honest, it's been a game changer. Traditional desks keep you locked in one position all day. Terrible for posture and terrible for productivity. The E7 Pro fixes that. It adjusts from 25 to over 50 inches, so whether you're short, tall, or just want to move more, it adapts to you, not the other way round. This thing is built like a tank. It handles up to 440 pounds, so heavy monitors, cameras, even my whole physics setup is no problem. And it's not just strong, it's stable. Watch this. No shakes, no spills, even at full height. The motors, quiet and smooth every single time. For me, it's about durability and simplicity. I just want a desk that works, and this one delivers every day. FlexiSpot is celebrating their 9th anniversary with up to 65% off. And if you mention Physics Explained and use the code on the screen, you get an extra $50 off at checkout. Seriously, if you're thinking about upgrading your workspace, now's the time. Grab yours at flexispot.com before the sale ends. So a big thank you to FlexiSpot for sponsoring this video and for saving my back. Well, a prime number is defined as a whole number greater than 1 that has exactly 2 factors, the number 1 and itself. They are the indivisible atoms of arithmetic. Every other number, called a composite, is made by multiplying primes together. To picture the difference between a prime number and a composite number, imagine you have 24 identical square tiles, and your goal is to arrange them into a perfect rectangle. In the case of 24 tiles, there is more than one way that you can do this. One option would be to arrange them in a 4x6 rectangle. Another option is 3x8, or you could arrange them in a 2x12. And finally, there is the trivial arrangement of 1x24. And so we see that the number 24 can be broken down into smaller composite factors, and hence it's called a composite number. But now imagine that you have 7 tiles, or 11, or 13. You quickly discover there is only one rectangular arrangement possible for each, 1x7, 1x11, and 1x13. Those are the primes. They resist being broken down into smaller composite factors. This mental image works for every whole number. Some can be factored into smaller factors, and those factors can then be broken down again until you're left with nothing but primes. And once you reach those primes, you can't break them further. They are the final indivisible shapes in the tiling game of numbers. For example, if we take that number 24, we can write this as 2 times 12, and then the 12 can be written as 2 by 6, and then finally the 6 can be written as 2 times 3. And so we end up with 2 times 2 times 2 times 3, and each of these numbers are prime, since they cannot be broken down any further. And the same is true of any composite number. For example, take the number 84, we can write this as 2 times 42, which is equal to 2 times 2 times 21, and we can break this down further and write 2 times 2 times 3 times 7. And here the chain ends, since none of these numbers can be broken down any further. We say that the composite has been factored into its constituent primes. And the incredible thing is that this works for any composite number, whether large or small. No matter how far you go, every whole number greater than 1 is either prime, or it can be broken down into primes in exactly one way. This remarkable truth is known as the fundamental theorem of arithmetic. And it was first glimpsed more than 2,000 years ago by Euclid in his pioneering work, Elements. It's a simple fact, yet astonishing when you stop to think about it. Most people have never noticed that the entire world of numbers is built from these indivisible building blocks, combined in unique patterns. And here is where the intrigue begins. Once you know what primes are, the questions start flooding in. Can you predict which numbers are prime? How many primes are there in total, or in a given stretch of the number line? Are they sprinkled about randomly, or do they follow some hidden pattern? But before diving too deep, let's start with something practical. Suppose you're given a number. How do you actually check if it's prime? Take 113 as an example. At first glance, you might think we need to test it against every smaller prime, but that would take far too long. Instead, there's a shortcut. We notice that 11 times 11 is equal to 121, which is larger than 113. That means that if 113 could be factored, one of the factors would have to be smaller than 11. If both were 11 or greater, then their product would already overshoot. And so instead of testing all primes below 113, we only need to check the primes less than 11, namely 2, 3, 5, and 7. And since none of them divide 113 evenly, we conclude that 113 must be prime. This is the essence of the square root shortcut. To check if a number n is prime, you only need to check primes up to the square root of n. For instance, to check 343, we note that the square root of 343 is about 18.52. So we only need to test primes up to 17, namely 2, 3, 5, 7, 11, 13, and 17. And if none of these divide it, then that tells us that 343 is prime. But in this example, we find that 343 is equal to 7 times 49, and so we conclude that 343 is composite. Now, although this shortcut is very powerful, for very large numbers, it can be very slow. And also, it doesn't help us answer a deeper question. How many primes are there? In physics, we believe there are only a finite set of fundamental particles. If the same were true of primes, then in principle, we could compile the complete list once and for all, job done, and never need to search again. Well, the question of how many was answered in around 300 BC by none other than Euclid, in a proof so simple and so elegant that it's been celebrated for over 2 millennia. His proof is a classic example of reductio ad absurdum, or proof by contradiction. You assume the opposite of what you hope to prove, and then follow the logic until you reach an impossibility. So let's assume for the sake of argument that there are only finitely many primes. Imagine we've managed to find them all and write them down in a neat little list. For example, 2, 3, 5, 7, and 11. Now, Euclid asks us to perform a very particular calculation. First, we define a new number p which results from multiplying all of the primes together. And in our example, we find that p is equal to 2310. This number p is, by construction, divisible by every prime in our list. Now, here comes the key idea. We add 1 to p. In other words, we define a new number n, which is equal to p plus 1, and so in our example, we find that n equals 2311. This new number n has a very special property. If you try to divide it by any prime in our complete list, you always get a remainder of 1. Divide by 2, remainder 1. Divide by 3, remainder 1. Divide by 5, 7, or 11, and in every case, the remainder is 1. That means n is not divisible by any prime in our list. And so two possibilities now exist. First, n is prime. In this case, we have found a brand new prime that is not in our original list, and our assumption that we'd listed them all was wrong. Second, n is composite. But in this case, its prime factors cannot be in our original list, since none of them divide n evenly. This means n must have prime factors that we didn't know about, again proving our list was incomplete. Either way, our initial assumption fails. There must be more primes than were in our list. And in our example, with n equals 2311, it turns out that n is indeed prime, and not contained in our initial list, which proves the list was incomplete and our initial assumption was wrong. Okay, so now that we understand the logic, let's try another case. Suppose this time we start with the primes 2, 3, 5, 7, 11, and 13. We then multiply them together to find p, and then add 1 to find a value of 30,031. Next, we check divisibility. 30,031 is not divisible by 2, 3, 5, 7, 11, or 13. In fact, 30,031 is equal to 59 times 509, and both are prime numbers, and neither appeared in our supposed complete list. And that's the genius of Euclid's argument. No matter how long a list of primes you start with, this simple construction always forces new primes into existence. There is no complete list. Our initial assumption that there is a finite list was false. The conclusion, there must be infinitely many primes. Euclid's proof is heralded as one of the great proofs in mathematics, but it doesn't just show that there are infinitely many primes. It even hints at a way to generate them. You simply multiply the ones you know, add 1, and new primes must appear. But brilliant as it is, this method is wildly impractical. The numbers explode in size almost instantly. That's why mathematicians, ancient and modern, have searched for faster, more systematic ways to find primes in the endless sea of integers. And more than 2,000 years ago, Eratosthenes of Cyrene devised one of the most beautiful answers to the problem of finding primes. His method, today known as the Sieve of Eratosthenes, is so simple a child can grasp it, yet so powerful it remains one of the most elegant algorithms in mathematics. To see how it works, consider every whole number between 2 and 100. The first step is to consider every multiple of 2. We then remove every multiple of 2 except for 2 itself. Next, we highlight every multiple of 3 and then remove these. And then repeat for 5 and for 7. And at this point we can stop, because what remains are all the primes between 2 and 100. Every composite number has been crossed out. This is the Sieve of Eratosthenes. What's left are the 25 primes less than 100, revealed by a process as straightforward as it is ingenious. But the sieve gives us more than just a list of primes. It gives us insight. Once the composites are filtered away, new questions emerge. For example, how many primes are there in a given interval? For example, between 1000 and 2000. Is it the same as between 2000 and 3000? Or does their frequency change as the numbers grow? For example, if we apply the sieve of Eratosthenes to the first 10,000 numbers, the list gradually whittles away as more and more composites are removed. And when the dust has settled, we find that there are exactly 168 primes in this interval. But why stop here? Can we push further? For example, if we count the primes in blocks of 1,000 numbers up to 10,000, a pattern begins to reveal itself. At first, this might not seem remarkable, but look closer. In the first 1,000, there are 168 primes, yet by the time you reach the 7,000s, 8,000s, and 9,000s, each block of primes is only just greater than 100. It appears as if the primes may be thinning out. So let's plot this data, with the upper bound of each interval plotted on the x-axis and the number of primes in the interval on the y-axis. Then there does appear to be a very gradual reduction, although it is by no means conclusive and it does wobble around a bit. Okay, but what if instead of blocks of 1,000, we looked at blocks of 10,000 all the way up to 100,000? What would we then get? Well, if we plot this expanded data, this time expanding our axes, we see the same steady decline appear, and it raises an unsettling thought. Are the primes slowly heading towards extinction? Could there be some point where they vanish altogether? At first glance, it almost feels that way, but Euclid showed us long ago this can't happen. However thinly they spread, the primes never end. This paradox, infinite in supply, yet dwindling in density, is our first real clue that the primes may be following a much deeper pattern. And this leads to a question so tantalizing it has obsessed mathematicians for centuries. If the primes never end, yet grow ever sparser, is there a law that governs their thinning, or a formula that predicts how many primes lie below any given number? To take a step towards answering these questions, let's repackage the data we were looking at earlier, which, if you recall, told us the number of primes in each interval of 1,000 all the way up to 10,000. Instead, we're going to list every 1,000 all the way up to 10,000 and call this x. In the second column, we define pi of x as the number of primes less than or equal to x. And if we count up to each number in the first column, we find the following results for pi of x. At first glance, it's hard to spot anything interesting in this new table of numbers. But if we plot the results, a subtle curve begins to emerge. The number of primes keeps growing, but it's clearly falling behind x itself. They're not directly proportional. Now, the resolution here is fairly low. We're only plotting 1 point for every 1,000 numbers, so we lose a bit of detail. If instead we were to increase x one at a time and count the number of primes less than or equal to x at each step and then plot the results, we find the following pattern. The graph you get shows the same overall curve, but now it looks jagged. Each jump in the staircase marks the arrival of a new prime. And if we overlay the smoother line from before, it still captures the broad trend. Okay, so let's go back to our table and attempt to quantify just how quickly the primes are thinning out. One way to do this is to look at the proportion of numbers that are prime up to a given value of x. In the first 1,000 integers, about 16.8% are prime. By 2,000, that proportion has already slipped to around 15%. At 5,000, it falls to about 13.4%. And by the time we reach 10,000, only about 12.3% of the numbers are prime. This fraction, written as pi of x divided by x, is the average density of primes up to x, and its steady decline is hinting at the fact that the primes are thinning out. Now, there's another way to look at this thinning out. Instead of asking how many primes there are up to x, we can flip the fraction over and ask about the average gap between consecutive primes. This can be written as x divided by pi of x, and we find the following results. At 1,000, the average gap between primes is around 6. By 5,000, it's a little under 7.5. At 10,000, it's just over 8. That's a surprisingly gentle rise. Across an entire order of magnitude, from 1,000 to 10,000, the average gap has only grown by about 2. But it's grown. It's a slow, steady climb. but it's a climb nonetheless. And we can picture this. If we plot a graph of x against x over pi of x, the result is a curve that rises quickly at first, but then slows into something steadier. The average gap between the primes is growing, but at a decreasing rate. And to a mathematically curious mind, it has the feel of something familiar. So the natural question is this: is there a rule that governs this steady increase in spacing? And if so, how do we find it? Or is it just a quirk of the first 10,000 numbers, one that disappears in the vast expanse stretching from 10,000 to infinity? To chase the answer, we need a very particular kind of curve, one that rises quickly at first, then slows, but never quite stops, stretching further and further without end. And here's the surprising part. You've probably met the idea before, not in mathematics, but in everyday life. It shows up in the way money grows inside your bank account. Imagine you invest £1 at 100% annual interest. If the bank pays interest only once at the end of the year, the outcome is straightforward. You double your money because 100% of 1 is 1, and therefore the total is exactly £2. Now, suppose the bank pays interest twice a year instead, every 6 months. The yearly rate is still 100%, but now it's split into 2 equal payments of 50% each. After 6 months, your £1 becomes £1.50. 6 months later, you earn 50% on that £1.50, an extra 75 pence, and so that £1.50 becomes £2.25. Now, we could have calculated the total in one go by writing 1 times 1 plus 0.5 raised to the power of 2, which is equal to 2.25, with the 2 in the power telling us that we have 2 compounding periods. Note that you've earned more with 2 compounding periods compared with 1 annual compounding, thanks to interest on interest from the first payment. Okay, so let's now apply this to some other cases. For example, if we compound 4 times per year, the 100% annual rate is split into 4 payments of 25% each, so the calculation is 1 times 1 plus 0.25 raised to the power of 4, which is roughly £2.44. What about monthly compounding, which corresponds to 12 times per year? Well, in that case, we end up with £2.61. Daily compounding would correspond to £2.71. We can see the pattern. The more frequently we compound, the higher the final amount. But notice that the gains are shrinking each time. The jump from yearly to half-yearly compounding is big, but from monthly to daily is small. Okay, so what happens if we go beyond daily? What if we compound every hour, or every second, or, in theory, at every possible instant with no gaps at all? In mathematics, we call this continuous compounding. In that case, the formula to calculate the final amount can be written in the following form, where the number of compounding periods tends to infinity. And in this limit, we arrive at a very special number called E, known as Euler's constant, which is approximately 2.718. And so, if you invest £1 at 100% annual interest, compounded continuously, you will end the year with exactly E pounds. Now, it's important to realise that this number isn't arbitrary. It emerged naturally, and with it comes a really simple rule. At 100% continuous interest, the final amount you would end up with after t years of interest growth would be equal to e raised to the power of t. And we can visualise this growth. Imagine a graph with time along the x-axis and your balance on the y-axis. At t equals 0, you start with £1, by t equals 2 it's £7.39, and by t equals 3 you've rocketed to about £20. The further you go, the steeper the curve. That's the classic shape of exponential growth. It starts off gently, and then suddenly it feels unstoppable. But there's another question we could ask, the mirror image of the first. Instead of asking, given the time, how much will I have, we flip it around and we ask, given the amount, how long did it take to get there? That's the reverse problem. And the tool for answering it is called the natural logarithm, written as ln of x. Now, here's what this means in plain English. If e raised to the power of t is equal to the amount after t years, then for a given amount, t is equal to the natural logarithm of the amount. This tells you how long it took to get there. The natural logarithm literally tells you how long it takes to grow from 1 to a given amount under perfect continuous growth at 100% interest. For example, if you have £20 and 9 pence, then the natural logarithm of this amount is equal to 3, and so it took exactly 3 years to get there. If you have £100, then the natural logarithm of 100 is about 4.6, and so it took about 4.6 years. Okay, so can we plot a graph to represent this information? Well, the answer is yes. It's essentially the opposite of the exponential curve. Whereas the exponential curve starts slow and then rises rapidly, the natural logarithm starts fast and then rises slowly. We can see this explicitly for the example we've been considering, with the total balance on the x-axis and the time in years on the y-axis. And we see a smooth, characteristic curve, with each new step in height costing more and more in width. And it is this shape, the shape of the natural logarithm, that we want to pay attention to, because hopefully this shape looks familiar and similar to something we looked at earlier. To tease out this similarity, let's plot two curves side by side. In the left plot, we have x over pi of x on the y-axis, and in the right-hand plot, we have the natural logarithm on the y-axis. And we clearly see the similarity in shapes. This was the curve we were looking for, and we found it in the world of logarithmic growth. Okay, so maybe the average spacing of the primes at a given value of x is in some sense approximately equal to the natural logarithm of x. After all, the shapes looked very similar. Could this be the law that we've been searching for? Well, rather than drawing two separate plots, let's put both curves on the same graph. First, we plot the data showing how the average spacing between the primes increases. Then we overlay the natural logarithm for the same range of x. And here's what we notice. While the shapes are similar, they don't perfectly overlap. The logarithm of x consistently gives values that are too high. We can see this even more clearly if we return to our table of data and add a new column, the natural logarithm of each x value. And if we calculate this, we find the following results. If we compare these values with the values x over pi of x, we see that they're close, but the logarithm value is always larger. But notice that if we calculate the percentage difference between the natural logarithm values and the actual values, we see that the percentage difference generally decreases as the value of x increases. Okay, so let's visualize what's going on. In the left plot, we see the two curves we compared earlier, and in the right plot, we see the percentage difference between them drifting steadily downwards. The trend is unmistakable. Although the natural logarithm over-predicts the average spacing of the primes, we see that the percentage difference between the prediction and the actual value decreases as we move up to 10,000. But the integers do not stop there, nor do the primes. And the evidence suggests that as we move further out along the number line, the percentage difference will keep shrinking. Okay, so let's ramp things up a bit. Instead of stopping at 10,000, let's look at a range of values each 1,000 times bigger than the last, starting at 1,000 and going all the way up to 1 quintillion. That's a million trillion, a 1 followed by 18 zeros. Then, as before, we count the number of primes less than or equal to x for each number, and then finally, we calculate the average space between primes as before, by dividing x by pi of x. Next, we calculate the natural logarithm of x for these larger values, and then work out the percentage difference with x over pi of x. And the pattern is as we suspected. the percentage difference keeps shrinking. At 1,000, it's about 16%, and by the time we reach a quintillion, it's down to roughly 2.5%. And that suggests something really profound. Maybe if we could keep going forever, the difference would eventually disappear. In other words, in the limit as x goes to infinity, the average spacing between the primes, which is x over pi of x, grows like the natural logarithm of x. Now, mathematicians usually flip this expression around and write it like this. And this is a remarkable expression. It tells us that as x grows larger and larger, the number of primes up to x, written pi of x, behaves more and more like x divided by its natural logarithm. Mathematicians put it this way: x over log of x tends asymptotically to pi of x. That's what the wiggly line, the tilde, really means. And it has a precise definition. It says that the ratio pi of x to x over log x approaches 1 as x grows without bound. In other words, the two quantities aren't just close, their percentage difference shrinks towards 0 as x tends to infinity. What looks like chaos and unpredictability when we zoom in on the primes, on the grandest scale, dissolves into one of the smoothest curves in all of mathematics. And this extraordinary relationship has a name: the Prime Number Theorem. Now, it's interesting to get a sense of what's going on by creating a new plot, this time comparing pi of x with x over log of x. And at the same time, we will plot the ratio of pi of x over x divided by log of x and see if this does indeed approach 1 as x increases. As you can see from the left-hand plot, the curve representing x over log of x always lies just below the line for pi of x throughout the entire range. In other words, it underpredicts how many primes there actually are up to a given value of x. But if we look at the right-hand plot, we see that as x gets larger and larger, the ratio between the two does creep closer and closer to 1. Now, this plot only takes us as far as x equals 100,000. To really be able to see what's going on, we need to go much, much further. To do that, we'll change the scale on the x-axis so that each tick mark represents a jump of 10,000 times larger than the previous one. And when we plot the ratio on this new scale, the trend becomes crystal clear. As x grows large, up to 10 to the power of 24, the ratio keeps edging closer to 1. And we can see that in the limit that x tends to infinity, it looks as if the curve will tend to 1. Okay, so that's the big overarching picture. But how did mathematicians first come to this idea? Well, like many stories in mathematics, the story of the prime number theorem is a fascinating one. The first published statement which came close to stating the prime number theorem was due to Adrienne Marie Legendre, who conjectured in 1798 that the number of primes up to x could be approximated by the following expression, where a and b were unspecified constants. In the second edition of his essay on the theory of numbers in 1808, he refined the conjecture, fixing a as 1 and estimating b as minus 1.08366. Legendre's choice of constant was guided by trying to fit the available data at the time. Rather than dividing by log of x, he shifted the denominator down ever so slightly and wrote the following expression. So what is the effect of this shift? Well, if we plot it, we see that this tiny correction makes a surprisingly big difference. By subtracting 1.08 from the denominator, Legendre effectively nudged the curve upward, bringing it into closer agreement with the actual prime counts. This might seem like a small adjustment, just a constant in the denominator, but across the available range of data at the time, the predicted number of primes tracked the real counts quite accurately. And this closer agreement becomes clearer when we look at the ratio of pi of x to Legendre's formula. We see that the ratio approaches 1 much more quickly than with the unshifted logarithm expression we considered earlier. But here's the twist. While Legendre was the first to publish such a conjecture, historians widely agree that the first person to truly notice the pattern in the primes was actually a 15-year-old boy. His name was Carl Friedrich Gauss. The evidence comes from a now famous letter. On Christmas Eve of 1849, at the age of 72, Gauss wrote to the Berlin astronomer Johann Franz Encke. In the letter, Gauss recalled how back in 1792 and 1793, when he was just 15 or 16, he had already turned his attention to the distribution of the primes. He had spent countless hours tabulating and counting primes in successive groups of 1,000. Regarding this earlier work, he wrote, "I soon recognized that, despite all fluctuations, this frequency is on average very nearly inversely proportional to the logarithm, so that the number of all primes below a given limit x is approximately expressed by the integral of 1 over the natural logarithm." What Gauss was essentially saying is that the number of primes up to x, which, if you recall, is pi of x, could be approximated by integrating the reciprocal of the natural logarithm. Okay, so let's pause and think about this. What does that actually mean? This is the first moment in the story where an integral appears. So let's take a moment to carefully unpack Gauss's claim. The natural place to begin is by visualizing the function 1 over the logarithm of t. If we look at the plot, we see that at t equals 1, it isn't defined, because log of 1 is 0. If you take numbers just below 1, their logarithm is a tiny negative number. Dividing 1 by that number gives a huge negative value, so the curve plunges downward. If you take numbers just above 1, their logarithm is a tiny positive number. Dividing 1 by that gives a huge positive value, so the curve shoots upwards. That's why at t equals 1, there's a vertical asymptote. The graph blows up in opposite directions on either side. Okay, so that's the function itself, but Gauss wasn't just thinking about the shape of this curve. He was thinking about its integral. And remember, integration is really about area. It's the running total of the area between the curve and the x-axis. So let's go back to our graph, but this time, let's shade the area between the curve and the x-axis. What we'd really like is a formula that tells us what that shaded area will be between any two values, because, according to Gauss, that would give us an estimate for how many primes are hiding between those two values. However, here's the catch. There isn't a neat ready-made formula for this integral, and so mathematicians gave it a new name. They called it the logarithmic integral and wrote it as Li of x. By definition, Li of x is the accumulated area between the curve and the x-axis, starting from 0 and running up to x. But there's a subtlety, because at t equals 1, the function isn't defined. So when we say the area up to x, we have to interpret it carefully. Mathematicians do this using what's called a principal value, which basically means adding the area from below 1 and above 1 in a balanced way. So what does the result look like? Well, if we slowly scan x from 0 to 10, and then in the bottom subplot track how the shaded area builds up, we get a curve. At first it's negative, but then from around x equals 1.45 onwards, the positive contributions begin to outweigh the negative ones. From there, Li of x climbs steadily upwards, with its slope at any point given by 1 over the natural logarithm. And here's the striking part. Once you're beyond that threshold, the overall shape of Li of x begins to mirror what we saw when we plotted pi of x, the prime counting function. And this mirroring becomes even clearer if we plot pi of x and then compare with the logarithmic integral on the same graph. And we see that the overall shapes match very well, and the relative error shrinks as x grows. We also note that across this range, the logarithmic integral curve approximates pi of x significantly better than x over log of x does, which is the green curve that's just been drawn in. What's truly remarkable is that in his letter to Encke, Gauss included tables showing he had investigated the distribution of primes up to 3 million, and then he compared his counts with values from the logarithmic integral. The agreement is striking. For example, in the interval from 2,600,000 to 2,700,000, there are 6,765 primes, while the logarithmic integral predicts a value of 6,761.32, which is impressively close. Another fascinating feature of Gauss's letter to Encke is his direct comparison between his logarithmic integral approximation and Legendre's formula with constant 1.08366. Gauss observed that over the range he examined, up to about 3 million, Legendre's formula produced slightly smaller errors. However, he argued that it was ultimately inferior, since the rate at which Legendre's error grew was greater than that of the logarithmic integral approximation. To see this in more detail, we can look at the range of values considered by Gauss, along with the values of pi of x. Then, if we use Gauss's logarithmic integral, we find the following values. And by looking at the difference between these and the actual values, we find the following list of error terms. Next, we use Legendre's equation, and we find that the errors are indeed smaller over this range. But Gauss spotted that the rate of increase in error was greater when using the Legendre equation. And we can actually visualize this. If we plot the error on the y-axis against the x values considered by Gauss, then the first set of data represents the logarithmic integral error and the second Legendre's error. And if we extrapolate, we see that at larger x, the logarithmic integral will have a smaller error than Legendre's estimate. And this is ultimately due to the rate of growth of error, as Gauss noted in his letter. The underlying issue with Legendre's approach, Gauss explained, is the fixed constant in the denominator. To keep the formula in step with the actual prime counts, that constant wouldn't really be fixed at all. It would need to decrease slightly as x grows. In other words, instead of a single constant a, you'd need something like a of x, a value that subtly depends on x. Gauss added that he dare not conjecture whether the limit of a of x as x goes to infinity is 1 or some other number. The numerical evidence simply did not warrant a firm claim. Now, as with a lot of his work, Gauss never actually published his investigations on the distribution of primes. Nevertheless, there is little reason to doubt his statement that he began this work in 1792 and 1793, well before Legendre's memoir. And it's remarkable to imagine his patience and persistence doing all of this long before the advent of digital computers. In Gauss's words, "I have frequently, since I lacked the patience for a continuous count, spent an idle quarter of an hour to count another 1,000 here and there, although I eventually gave up without quite getting through 1,000,000. Now, I challenge any viewer to manually count the number of primes even within an interval of 100, let alone close to 1,000,000. It really is mind-boggling." Okay, so where does this leave us? Well, all of these comparisons point towards the same big picture that Gauss identified, that the primes thin out at a rate governed by the reciprocal of the logarithm. Now, it's important to note that in modern number theory, it's standard to define the logarithmic integral with a capital L, and we write Li of x is equal to the integral from 2 to x of 1 over the natural logarithm. Starting the integral at 2 avoids the singularity at t equals 1, and it reflects that primes begin at 2. With this convention, the prime number theorem can be stated in either of two equivalent ways. Firstly, pi of x is asymptotic to x over log x, and secondly, pi of x is asymptotic to capital Li of x. And as noted earlier, this is equivalent to saying that the ratios both tend to 1 as x tends to infinity. This is the rigorous form of Gauss's insight. And we can illustrate this numerically. If we plot the ratios, then we see that both curves tend towards 1 over the range that we can compute. This is suggestive rather than conclusive. Numerical evidence is not a proof, but it visualizes the trend that the theorem asserts. Okay, So we now have an understanding of what the prime number theorem is claiming, but mathematicians didn't want to just conjecture, they wanted a proof. And the next big breakthrough came in 1859, when Bernhard Riemann published what is often called one of the greatest mathematical papers ever written, on the number of primes less than a given magnitude. In just a few pages, he reframed the entire problem, introducing the zeta function as a new lens on the primes, and ending with a bold conjecture, the Riemann hypothesis, the statement that all non-trivial zeros of the Riemann zeta function have a real part equal to 1/2. More than 150 years later, it remains the most famous unsolved problem in mathematics. Riemann's insight set the stage, but the proof of Gauss's prime number theorem would have to wait another generation. Finally, in 1896, working independently, Jacques Hadamard and Charles Poussin finally established it. As numbers grow, primes thin out in a steady, predictable way. The rule of thumb Gauss glimpsed was not just a good fit, it was the truth. And with that, a mystery stretching back to Euclid was finally resolved. And here's the real lesson. Even in pure mathematics, the most abstract of human pursuits, progress can begin with data. Gauss didn't just dream, he counted, he measured, compared and tested. He let the numbers speak, and then he followed them. That is mathematics at its best. Respect the data, test your ideas, and only then dare to conjecture. And I think it's only fitting to close with Gauss's own reflection. It is not knowledge, but the act of learning, not possession, but the act of getting there, which grants the greatest enjoyment. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much, I couldn't do it without you.